Awesome. Artem, thank you so much for joining us to present today.
Sure.
Very excited about this. I've always wanted to be even a novice at Haskell and have not accomplished that yet. But maybe learning about some of these mathematical foundations will help me to learn some Haskell for great good in the future. So we appreciate you coming to talk to us, and I think I'll just give you the floor. So thank you very much.
Sure. Hi, everyone. Yeah, I'm happy to present this topic, which is, Haskell is a long-standing passion of mine. I'm not doing any research around it currently, but maybe someday, I don't know. So this work is done. So the linear Haskell work in particular was done during last 3 years, maybe a bit more. So relatively fresh. As for the mathematical foundation that you mentioned, Max, I don't really plan to show much of math. Well, actually, any of it. I thought maybe it would be, easier to get it through the code instead of the formalisms. Although there is plenty of formalisms around Haskell, as you pointed out. So let's see. So there are two parts of this phrase, linear Haskell. There is the somewhat well-known, somewhat old programming language called Haskell. Appeared like 30 years ago about. And there is the linear part, which appeared only recently. And so I'm going to start with discussing the linear part first, because, Haskell is a programming language like many others. And linear types, which were added to it recently, is a rare feature. So why anyone should care about this feature? That's the question. So there are a couple of points here. First one is well-typed resource-aware protocols. So the easiest example is when you open a file and you have a file handle to work with that file, and you write and read, and do all sorts of things, and then you, in the very end, you're supposed to close that file. Not everyone does it. Sometimes it even works, but sometimes it doesn't. So the problem is, of course, well known and been around for decades. Several languages have some special purposed language constructs to handle this problem. Most of them based on the notion of scope. So you can introduce certain scope inside your program, and then only in that scope that file is alive. And then when the scope ends, you get your file closed automatically for you. That's how it's done in several languages. The most, I think, the earliest that I remember of mainstream languages was C# that added it. I think after that it's spread through several others. This has benefits, of course. It's better than plain old C kind of interface. When you have the open function and the close function, it's up to you if you call close after open or ever. And but it's still up to the programmer whether he or she uses that kind of special purpose construct for managing resources. And it's definitely not for any kind of resources. So it usually doesn't scale very well for user-defined types. Sometimes it does, though. Still, a sort of ad hoc solutions are around. And principal solution was suggested also decades ago in Girard's linear logic. And then several people who developed this idea further. So I actually have a name of one of the guys who contributed to this idea a lot, Phil Wadler, one of the big PL guys. And so he wrote this encouraging paper in 30 something years ago that says that linear types can change the world. And it didn't really at that time, and it still probably hasn't. But we will see. There is a third bullet point in this list, which points to some changes in this. So what Wadler said is actually interesting, because there are two paragraphs in this quote on the slide, and one of them is, so the first paragraph says, let's divide all values into two groups. One are classical values that you can process just as you did before. And the other one is linear values, like files, database connections, network connections, stuff like that. And that group will be handled specially according to these rules of linear logic. So in the outset, it's a very intrusive approach that you have to, come to a language which has only one notion of type and say, now you have two different notions of types. And they are like, it's not clear how they will interact, how the programmers will figure out which one to use, and how they interact between each other, stuff like that. So this is a very ambitious proposal, wasn't really implemented that like in this particular form. But there is a second paragraph here, which says that, in fact, so actually the first paragraph also says that if you're smart enough, you can avoid garbage collection for the second kind of values, the linear values. And that should ring some bells to someone who was, tracking the programming language space lately, at least last several years. And the second paragraph should ring the same very bells, which says you don't really. So for linear values, it's actually not necessary that you have the unique sort of property that only one person has this value, and they will be in charge of closing that, like cleaning up that resource or closing that file. So as long as several people sharing the resource only read from it, it's okay. And only when you need to write to that resource, you will face all the consequences, and you actually should be the only one who owns that resource at that point. So if I wasn't wasn't clear enough, so I'm actually pointing to the Rust side, right? So there is this programming language, much younger than Haskell, less than 10 years, I think. And it actually implements both of those ideas that given in this paragraphs from Wadler. It does not have a garbage collector. It allows sharing for read-only values, and their sort of write values should be exclusive. It doesn't do this to divide types into two family thing, which is, as I said, very intrusive. So Rust instead has this idea of borrowing, which allows this, sharing read-only values and stuff like that. So all in all, Rust seems that I've been rehashing Wadler's paper recently, and I thought, well, Rust really comes quite close to what was the idea behind it. Okay, so why not Rust then? Why am I speaking about Haskell in particular? So Rust is a nice language, but not my favorite, because it's first, it's quite low-level language in my opinion. You really need to think hard about managing all those values and their lifetimes. And Rust actually cheated a little bit in the way that it created, so it's a new language. It was created from scratch. And that's that's cool, but still, ask yourself, can we take an existing language and retrofit the idea of linear types into it? So the guys working on Haskell and its sort of foundations and both implementation thought, well, Haskell has been a laboratory for programming language research for decades, so why not try it? And they have been trying for a while, and it's only, lately, as I said, they actually managed to build a reasonable prototype. And it has all sorts of problems that they had to solve all sorts of challenges that an existing language surviving this sort of huge change would face, right? It has all the code base that is not linear. It has libraries, idioms, and yeah. So and it's actually quite large language. This Haskell thing, right? It has a lot of syntax in it, so it's really hard to figure out how all the bits and pieces of it will interact with linearity. So that's a sort of a challenge on it itself, right? So it's one thing to build a formal model like Gerard did in the 80s or Wadler in that 1990 paper, or what Rust did, but this is a very different sort of challenge. Take an existing language and try to implement linearity in it so that the world doesn't crash on your head. And that's why it's sort of interesting for me. And speaking about our lab in Northeastern, many people work on this kind of more real world-ish problems, like how to change languages that people already use, how to make them better instead of building new languages from scratch. Yeah, and so I will try to show you how this worked for Haskell at least.
Artem, can I ask a quick question?
Yeah.
How does the difficulty of doing this for Haskell, or the challenges that I guess you'll shortly explain to us, how does that compare to like other languages? In other words, is Haskell sort of representative in some sense of a choice, or would it be completely different if you were to do Julia or I don't know, JavaScript or something completely different like that?
That's a very good question. It's always the question when people even build a new language for some, like to model some feature. Mm-hmm. It's always the question whether it will be realistic, whether it will be possible to put it on someone else's head. I really don't know. I'm not sure. As I said, it was an aspiration for Haskell for many years to be this laboratory for like new features in programming languages in general. And that's why they mainly, I think, tried it. So they actually push a lot of stuff into the language. Some of it just dies out at some point. Some of it survives. We'll see what happens with linearity. But yeah, as to other languages, it really, I think it takes an expert in another language to figure that out. Yeah.
Okay, I think there's another question.
Oh, sure. Yeah, can I ask one more question? So would you mind saying a little bit more about why we want linear types rather than just how we can get them working? Because going back to your opening a file example, in C, it seems like, oh, you can run a function to open and run a function to close, and that's perfect because now you can use your file in whatever way you need. And then languages like Python say, oh, we're just going to put this in a block, and we're making a language choice for you to try to open and close files in sort of small sections. And even though that doesn't give you all of the range of use cases you can do, it seems like a good enough idea and means people don't have to remember to close their file, which is a definite problem. Can you give a little more context about why we'd want a linear type in a situation like that?
Sure. Yeah, that's a very good point. I tried to touch upon it, but maybe not clearly enough. So the idea, the blocks that you mentioned, is what I referred to scopes earlier, but it's the same thing, really. So the problem with this block-based approach is that it is really on programmer to, like, whether they will use it or not. So I'm not sure about Python, but like in many languages like C++ or Java, which have all the same problems with the files, you can perfectly use files without any kind of, this blocking sort of guardian constructs, and then you will probably at some point forget it. And you can't really, so if you get to a code base with a million lines in it or something, it's really hard to check if any file interaction in that code base uses that blast solution. There is no sort of compiler support from telling you whether programmer adheres to this safe idiom or not, or they just think that they're smart enough so that they open file and they will remember to close it. So that's why anything that connects to typing is really a step forward in my opinion, because typing discipline will be checked of course, if you have a dynamic language, probably not, but even Python these days introduces some type checking, right? But in languages like Java or C#, you would have a type checker check it for you. And if you use, it will force you to adhere to safe idiom, so to speak. So it's a like if you so it will check that you are using the right thing. If you check that, it will check that you're closing your file.
Okay, and how does a linear, sorry to make it flesh it out, but like how does a linear type actually do that? Do you still use the same constructs to open and close a file, but you have this like special type that tells you when you're doing something wrong? I don't fully understand. Yeah,
so just like regular types, right? If you have an let's say you have a string and you try to put two strings together with plus operator and it doesn't work, the type checker in a statically typed language at least will tell you that it doesn't work. So the same very mechanism, and that's why it's sorry. Yeah, so I just read something from the chat and thought about Python. I was thinking about Python now.
Sorry about that.
No, that's fine. That's fine. Yeah. So the idea is typing discipline is something that is checked by the compiler. You're still using mostly the same constructs and the same language. Of course, there are some changes. That the whole point of this talk that it's not easy to retrofit the linear types into a language, but it still feels very similar. It's still the same open and close, but yeah, exactly. The type checker checks that you are doing everything right, like in a nutshell. And in details, I will try to show you later.
Okay, great. Thank you.
Sure. Yeah, and the other benefit is performance. So Rust is really known for its, low-level sort of target when it competes with C in performance. And that's exactly because it doesn't use the garbage collector, and it tries to be as close as and that's what allows it to be as close to the hardware as it can. And yeah, but the absence of garbage collector in turn was brought by this linearity discipline that it actually also implements in a way. Yeah, so performance and safety are two big things. But it's really, so maybe it's really, it's a little bit up in the air right now, but yeah, I hope I will show at least some of it at least in the Haskell example. Yep, so for Haskell, one of those things didn't really work, which is the runtime performance bit, or improving runtime performance. So I should spell it out. It's the idea that you can improve your runtime characteristics just avoiding garbage collection for linear values. Why is it possible? It doesn't matter as much right now because it's not implemented in Haskell. The reason of that is exactly the backward compatibility, because most of Haskell work is not linear at the moment, and it probably will not become linear ever, like most of it. Some of it probably will. But when you have these two kinds of values, and most of them are actually regular plain values and they're not linear, it's just much easier to manage them with garbage collector. If you really need the performance, you go Rust. And then you have to think about every lifetime of every value in your program, even for simplest one like integers, strings. You don't really want to care, strings usually are usually are allocated on heap, but even integers, those are small things that you shouldn't be thinking about their lifetimes at least. But in Rust you have to think about everything. You have to think about runtime of everything, right? And that's a challenge, but you'll get performance for that. Yeah, so not the case for Haskell. Let's see. So what I'm gonna be doing next is a quick Haskell intro, because I'm not sure how much of Haskell you know. I did this short poll which shows that I don't really need to do much of intro to Haskell. Fortunately, I don't really want to, but I will sort of rehash certain things that I really need in the next parts. And the next parts are, the main part is the linear Haskell compiler extension that's been around for at least in the paper for 3 years, and it was shipped with the 9.0 version of the GHC compiler this February. And then the later part of the talk is, if we get there even, is another neat idea about linear constraints that frees you from some of the sort of bookkeeping that linear types puts on you, but really quickly. And it's still it's in submission. I'm not sure it's a fully worked out idea, but it's a nice one, I think. And then Q&A, but yeah, please jump in with your questions. I would really love to have it, conversation style, not the presentation style. We don't have to go through whole thing because it's not my research. I don't really need to present, I don't have burning desire to present everything as it happens to my research usually. And yeah, so basically I'm happy to chat, discuss certain things. If they come up to any one of you, please just bring them up. I hope I have chat in my computer available. I didn't see. Not sure
also
why.
People can just unmute and say, excuse me, I've got a
Yeah.
question. Yeah, if anybody, I think everyone here has attended prior events, but if you haven't, we're a pretty informal group. So feel free to just unmute and ask your question.
Yeah, I'm happy. Yeah, I'm happy to chat. Please feel free to unmute. I'm saying about chat just because I personally usually find it easier to not, to just type in something and then see if the presenter will see it fits. They will bring it up. But yeah, any either works for me. Doesn't really matter. All right, so let's move on. Yeah, what is Haskell? So I took this not literally, but close to the Haskell report, which is the sort of language standard at this point. And they have a huge number of features that they claim Haskell has. So what I want you to do now, let's try to do a short sort of introduction thing. Try to think about your favorite language. Try to take one. I know it's hard. For me, it will be Haskell. For you, maybe something else. And let's try to go through every feature and just bend your finger for every feature that your favorite language has. I'm just curious how many you will have bended. So Haskell is a general purpose language first. means like if you like SQL, for example, it doesn't fit that bill, right? Still fine language. Most of language people know about are probably general purpose. It's a purely functional language. So there are two parts of this thing. First is functional programming language, and then purely. So there are a lot of debates these days, at least on the internet, of what can be counted as a pure language or purely functional language, and what can be counted even just a functional language. Maybe this day it doesn't even matter that much. Like many languages have functional features in them, right? So let's try to, so purely means something like you don't really have side effects in it in the language, but in Haskell you sort of have them. Not clear. So we will talk about a little bit how it works out in Haskell. So let's try to think if your favorite language is pure. I don't know of much of pure languages, honestly, and if it's functional. Now, featuring higher order functions. That's one of the features that I sort of mentioned is everywhere these days. And it's really hard to find, I think, a language that doesn't support higher order functions these days. It means that functions can accept other functions as parameters and can return other functions. There were days when some languages could accept other functions, but not return them. That was, yeah, tricky designs, but these days, most languages don't really restrict it. So it's the fourth one. So the fifth one is non-strict semantics, meaning that you don't necessarily evaluate the function arguments before you enter the function call. And that's also not very widespread feature. Although in many languages these days you have a kind of lazy semantics in some sense, in some places. For example, in Scala, they have lazy values. In many languages, even in Java, they have streams that claim to be lazy also. And non-strict is very close to lazy in some sense. It's like there are differences in details, but yeah, it's basically it. So please try to, yeah, so someone wants linear stuff, I see. Okay, so let's see. User-defined types, algebraic data types, I will show you them shortly. Module system is, yeah, Haskell really doesn't have a good module system, although, okay, they claim it, fine. Monadic IO system has to do with purity. So they don't get to just print stuff to the console at every point of the program. They will, yeah, there is something special to sort of communicate with outer world. And there is a rich set of built-in things. It doesn't really matter. Okay, so there are 10 things, exactly how many fingers you have. Hope you got over 5. Has anyone not got over 5? Okay, so Max says he got 5. So, okay, cool. 4, Jacob says 4, okay, it's also good. Okay, let's probably proceed to a simple example of a Haskell data type called list. So it's a user-defined type, although there are built-in lists in Haskell, of course, but I just want to show you some syntax. You know, there is a definition of the data type list. It has a type parameter a, so you would expect that lists can be, you know, lists of integers or list of strings or list of bools, stuff like that. And this list data type has two constructors. First is to construct an empty list, which is nil, and the second one constructs the const cell, which has 2 fields in it. So the constructor has 2 arguments. First is the value of type A, and second is the tail. So it's another list. So that's a definition of some simple data type. It's parametric and it's recursive in this case. So it's not the simplest example you can think of, but still. Let's see. I will use it a couple of places in this talk. I will use the GADT syntax, which is a fancier syntax for the same things basically. They're actually more general. So GADT means generalized algebraic data types, and they are more general than plain data types, but it's not really important for us right now. So let's look at the full equivalent of the list data type, but written out in the GADT syntax. So nil is the first constructor. It has type list A, and then the cons is the second constructor, has type list A to list A to list A, and it returns you or constructs you a list A. Hope that's fine. And just for again warm up, simple function that process lists. No matter which syntax you use for definition, they're absolutely equivalent, as I said. So the concat function concats two lists. So first line is this function signature here. So concat double colon, and then the signature, meaning that it takes two lists and returns a list as a result, defined by what's called pattern matching. So first it says if my, so the second line here and this last listing is concat of nil and something else is that something else, wise in this case, and the concat for const cell is the result of it is another const cell which takes x and recursively calls concat on the rest of the first list.
Artem,
yeah.
The only functional language I'm any good at all is Coq, and in Coq, my intuition, if you showed me something basically like this, would be that if I unfolded cons in the first definition, I would get the second definition or something like that. Is there some relationship like that, or is it just that they in what sense are they equivalent basically?
They are exactly the same. They will compile into the same code.
Okay.
So in this particular example of a list, it's the distinction is just pure syntax, no semantics.
Okay.
You can use one or another at your preference. It's funny you mentioned Coq because actually GADT syntax came from dependently typed languages. It was very popular there at first.
Okay.
And then it started in early 90s, and then it transferred to just functional languages. First Haskell and then a camel also get it. It's just a little bit clear, so you can, well, some says it's a little bit clear. You can read the type declarations just like you read type signatures for functions, right? So it feels like a constructor is kind of like a function. To be honest, completely honest with you, it's not exactly the same thing as the function signature. There are certain restrictions. So some things you can put on function signatures, but can't put on the GADTs and vice versa, I think. But that's, again, that shouldn't bother us at all at this point. You can perfectly think of them as just a constructor. It's a function with this particular type.
Okay, thank you.
All right, sure. So hope this makes sense. That's a simple, plain functional programming. I will need a little bit of type classes and monads in particular. So let's get through it, I hope, quickly again. So, famous last words, let's get quickly through monads. So what do we have here? So first is the class keyword, which means I am defining a sort of an interface. If you ever used any object-oriented languages, it's very similar thing. There are important different, but first approximation, I think it's a good thing to think about it as an interface with two functions in this case. So one function called return. So in order for a type M to be a monad, it has to define the return, the first function in this interface, and the bind is the second function of that interface. Bind is written funky. It's parens and some Unicode stuff, or it's ligatures in this case. It doesn't matter that much. You can call it bind. So everyone calls it bind. But yeah, it's what is it? Greater than equals sign. That's what you can do in Haskell for regular functions. You can define operators like that. You just use parents around this funky sequence of characters. And there are rules that says that you can do these names, but you can't do some names, some reserved names. So for monad, it says, yeah, so for bind, it's a little bit, so I'm not sure why I have for all here, just forget about for all. So M, actually, even from the return type, you can see that M is a parametric type, like our list used to be. So remember, we had list A, and that meant list of some types, like list of integers or something. So here, M of A says that it's M is some type constructor like list. So it's M of A, it's some constructor of A's. Like list of A's maybe. So actually I have an example of list exactly can be viewed as a monad. So we had this interface on the top. So now we have an implementation in the center. So for the list constructor that we defined on the previous slide. So it says that return is a cons of A and nil. So it's just a singleton list, right? And the type, so I hope it's kind of clear that the types work out. So you will return a list of A. So M of A in the sense of the interface. And there is the definition of bind that uses concat. Doesn't really matter the details. So we are able to implement list, an instance of monad for our lists that we defined earlier. So why I wanted to show this, like a quick refresher, that monads are a little bit special in Haskell because you can use do notation with them, or for types that has the instance of monad. So what does it mean? So do notation is just a syntactic sugar. So it will desugar to just calls to bind and return. So like nothing special, it's just very handy notation to use. So in this example, it's you first fire A, you get a result, and then you apply F to that result, and then you get another roped value, as I assume, because roped in the monad, right? And then you bind the result with that second action with Y, and then you return the result of G of Y. And that's exactly, so this sequence of actions or sequence of applications of, sequence of actions, let's say, is just a syntactic sugar for several binds. So the last line shows that you can say A bind the lambda, and then in that lambda you have the parameter X, and you apply F to X, and then you call another bind, and so on and so forth. So it's a very handy notation to use this interface. So why, questions about it? I'm gonna switch to the next slide, which is still about monads a little bit more, but yeah, hopefully it makes some sense. So why we care about monads in a pure language like Haskell? You don't get, like, you can't implement side effects. You can't implement a function that read a line from the terminal, but you can have a pure interface to actions that do the same thing. And it's just someone in late 80s, Eugenio Moggi, I believe, and then Phil Wadler popularized this idea that you can use monads to nicely rob that impure interface, or rather that impure world like terminal or network or database connection. You can rob it into monad and sort of interact with it as if it was a pure functional interface. So here I show you how to open a file and read the line out of it and close the file. So that's, we are coming closer to things that we mentioned during the intro when we speak about linear types, right? So here I use do notation, as would basically anyone using Haskell would use here. And yeah, so every line is called to impure function. Well, impure function, but it looks very nicely. It works just like a functional, language with many things. Like you have a higher order function, you have certain rules about this monads things. So it's a nice interface to an impure world. That's what we need for now. That's basically it. Okay, so that I think concludes my crash course in Haskell. And now I'll try to go into the actual linearity. So as I mentioned before, linearity in Haskell don't really bring you any performance benefits, at least at this point, but it allows you to express interesting contracts in your interfaces or in your modules. So here is just an example of kind of contracts you can state using in this case, so if you look at the sort example, so remember I told you the function signatures here are very important. So first line is the usual sorting function, you would say, and the second line, instead of the usual functional arrow, has this nice little, people call it lolly. It's, I guess, short from lollipop. And I think in papers, they usually call it just linear arrow instead of the regular arrow. So what is this linear arrow thingy? Yeah, and actually the example about sorted lists are a little bit involved, and there is a nice blog post explaining you how to do the sorted lists contract. But the other two contracts I mentioned here, which is the in-place updates and file handles, I hope to show you at towards the end, let's say. So what is this linear arrow thing? It says that it kind of acts like an arrow, like a usual functional arrow, which means you have an input of type S and you return a result of type T, but it has another sort of benefit to it, which is if the result of the function is consumed only once, then it guarantees that the input is also consumed only once. Remember, it's a lazy language, so here when you apply function to something, it doesn't get evaluated instantly. It will wait until at some point it will really need the result of this application f of u. So consumption here is a very delicate notion. There is a formal or semi-formal, I would say, definition of consumption. And it depends on what kind of value, like what kind of input types you have. For atomic types like integers, it says evaluated. So what does it mean to evaluate a thing? It means either apply a primitive operation like addition or print it to a console or something like that. So really apply some operation that really needs its value. And so for function, we will not use it much for functions, but for algebraic data types is what is important, at least for this talk, is that if in order to consume a value of algebraic data type once, you pattern match on it. Remember, like concat pattern match on its first argument to see if it's nil or cons. So that is a kind of pattern matching I'm talking about. And so if the constructor in turn has any linear arguments, and we will talk about that a little bit because constructors will have either linear or regular arguments or classical arguments. Then so you will have to consume all of the linear arguments once also. Hope this definition makes some sense, but it's really, yeah, the examples is what I think helps to understand it. So I'm gonna just go through a good bunch of examples to get you some feeling of what it means to have this small linear arrow instead of the regular arrow. So get back to our list example. Notice here I use the GADT syntax, and instead of the usual arrows, functional arrows, I use the lollis, which kind of means that the fields of my list constructor can guarantee this linearity thingy. So again, what it means will be probably clear if we get to the example. We get to our old friend concat at this point. And concat actually a function that does satisfy this requirement to consume only once, and actually both of its arguments. So let's see. So concat, so again, what's important here is the function signature, where I use two lollis, which means both arguments are linear. And so, but I do not change the definition at all. So the same old definition works. Why is that? Let's see. So first argument, I definitely, so let's say first line and first argument, I definitely pattern match on the first argument, but then I don't do anything with y's. Is that good? Does it not violate the, the consume once requirement? So it does not, because it turns out if you return something, it also works as consumption. So in particular, if you imagine an identity function, which just returns its argument, so it's a nice example. I didn't put it in the slides. So if you have the identity function and it just returns its argument, you can type it at the linear arrow, not just the regular arrow. Of course, you can also type it with a regular arrow, but like the linear arrow contract is a stricter one, because it has this consumption, requirement, one consume once, which the regular arrow doesn't, right? So, and the second line is kind of the same thing, except the whys, again, the fate of whys here is interesting. So you pass it to another call of concat, the recursive call of concat, and that also counts as consumption. So that also wasn't on my definition, but it sort of, naturally follows from it, I would say. So if you pass some linear argument to some function that also wants a linear argument, that counts as a consumption. Okay, and consumption once exactly. So if you had another function that accepts some list but doesn't get you that guarantees, the linear guarantee in particular, then you wouldn't be able to call it, because no one knows what it will do inside it, right? All right, so I hope this makes some sense. If you have any questions, so we haven't had questions for a while, so I'm getting a little bit nervous, but let's see how it goes. Okay, so that's not happening. Okay, yeah, that's fine. Let's see. So what's interesting here is that the backward compatibility story. So what should the plain old data types, how should the plain old data types behave? Should there, so here's the old definition of list. I call it list one, just no good reason. So do we think that, do we count the cons1 cons1 parameters as linear or not? So what's better? Like, what is it from the backward compatibility point of view? Does it make more sense to stick to the old one, say that there is no restrictions, no anything, nothing changes about the old plain old definitions? Or on the other hand, we can assume that all the fields again are linear. So it turns out that for backward compatibility, like for old code, it doesn't matter at all because it won't be able to observe the difference at all because it doesn't have anything in it saying anything about linear guarantees. So it just doesn't care. And one important thing that I should have said before is that the semantics, the actual compiled code, do not change at all, whether you have a linear function or linear field of the constructor, or you have the regular function or the regular field of constructor. They will compile to exactly the same code, binary code. So for a better sort of interactions with the rest of the language, it's nice to have the linear fields by default, it turns. So for gadgets, unless you turn on the extension, it's also all linear. If you do turn on the extension, then it's up to you to figure out which fields you want linear, which fields you want, classical. Let's see. Pairs. So another.
Wait, I have a question. Sorry.
Cool.
Sorry. Sorry. I'm in a bit of a pickle. I can't really talk too easily. So in the concat example, I'm wondering, is the rough idea that every site of pattern match on the left of the equal side is essentially like garbage collecting safely those references, and so it's sort of like destructing those items, and then on the right side each use of a nil or cons is, or I guess not even the nil or cons, like the y's or the cons is essentially building up and the results, and then like in cons x will then be discarded and the result will be the last thing left.
Wow. So let's see if I understood correctly. So first, there is no implications to runtime semantics of this extension, which means all will be garbage collected just as, plain old Haskell 98. There is no really difference. So the difference is only in type checking. And so the type checking is very early at the, the compiler pipeline. And it's the only phase where you can that can shout out it, that can scream at you if you do something wrong. And what does it mean to do something wrong? So for example, let's say in the first line, the concat nil part, if you could say equals nil, right, instead of y's. So in that case, the type checker would shout at you because you haven't consumed y's. But that, again, is just how it is defined in the type checker. It doesn't have any impact on the garbage collection. Does that make sense?
Yeah. I think I was just using garbage collection as like a way of sort of thinking that the type would be, or like that reference would just essentially be unusable. But yes.
Yeah. So maybe one more thing is that there is no clear benefit from using linear types in this example, really. So you could just use the same, old types, and they would just work. One thing though is that as I said before, if you just instead of y's put the nil there, it wouldn't be correct implementation of concat probably. And it wouldn't type as a linear value. So it seems it's like people who wrote some linear code or like some standard library in the using linear type, and say that a lot of algorithms actually it's much harder to get them wrong if you put the linear arrows in the proper places. And so for concat, if you think abstractly about it, it should use all of its arguments and should use them exactly once. It shouldn't try to, duplicate the second list or something like that. So it just helps you at this point. It helps you a little bit to not screw up your implementation. But again, it's all at the type level, not like nothing, nothing about garbage collector really applies.
Cool, thank you.
Okay, so pairs are a classical data structure in functional programming. So how do we go about them, for example? So as I said, all data types are linear by default, unless you really tried hard to, make them nonlinear, and we'll see why that would be useful in a bit. But here pairs are also linear. So in the first example, your function type is the regular function, so you can do whatever you want with your arguments. So none of the actually this consumption business requirements apply. So you can safely, in the case of F1, you can easily duplicate the first part of the pair and throw out the second one. So exactly because you have this functional arrow, like the regular functional arrow in the signature. Whereas in the second example, the F2 example, you have the linear arrow in the signature, and that means that the input should adhere to that rule. Remember, it said you should pattern match on the input, and here is the pattern matching, and you should consume all its linear components exactly once. So in no way you could do the same thing as you did for F1 here for F2. So you could swap, which we do here. We swap first and second component, but we couldn't do so if we wrote the same implementation as for F1. Again, type checker would be really unhappy. All right, so someone says they had to run, and it's already 6. Oh shit! I know I was very so Max. I know I'm very slow. Tell me what I should do. I could I don't know, show you maybe one example of the linear resource stuff, or I don't know. What's your thoughts?
I'd say do whatever you prefer, unless people in the chat voice an opinion. We should probably try to wrap up in the next 30 minutes or so, but
okay.
I'm perfectly agnostic, whatever your preference is.
Okay. Yeah, so my plan is to at least go to the 20th slide. I hope I will get there, and that's, I think, is where I have my main part ended. So let's see. So linear pairs. If you don't get anything, please ask. I hope it's clear. So the second example is the unrestricted thing, which I mentioned. Sometimes it's advantageous to explicitly ask for a unrestricted resource. And in that case, so you have to use the GADT syntax. Like for this UR, unrestricted, they fight a lot to figure out what's the better name, but they ended up with R or UR, I guess. And so for the second example, so for F3 here, we do get the linear pair as the input, but the second component of that pair is marked as unrestricted. So it means that you have to pattern match on UR to adhere to the consume once requirement, but you don't have any obligations about the argument of the UR constructor. And so you can just drop it. So here I just forget about, so underscore means I just forget about it. And it is okay, spoiler. So sometimes you really want this R to sort of allow you to drop certain things or duplicate, so like do certain nonlinear things with your values. So let's say, so I have several examples how linear arrow and a functional arrow, play with each other. So for example, first is here I show that if you have a linear function f and the nonlinear context, the classical context g, then the g's parameter is not bound to any requirements. So you can put it like you can push it into f, and f will be happy to accepted. So it's it shows that the linear arrow is not requirement to the caller of f in this case, but it's requirement on f itself, on its implementation. That's a sort of important difference. If you know Rust, it's really different from what they have in their system. I will skip this and probably, so, okay, so this one briefly, higher order case where G, so it's kind of like the previous example, but G has a higher order argument. So a function that takes int and returns an int. And the question is, can we call G with f? Because f, as before, has this linear type. Or in someone who thinks with, thinks in subtyping, that's actually just asking if linear arrow is subtype of classical arrow. What do you think? Is it safe to call it like that? Like, does it make sense? Okay, I wouldn't, yeah, okay, I'll tell you. So the idea here is that it is safe, but it's really hard to make type checker think so. So what GHC does in its implementation, it does something that's called Eta Expansion. So it transforms GF to this G of lambda. And lambda, you see, is a very simple thing. It accepts X and pours it into F. So this thing is mostly equivalent to the legal question mark thing, but it's easier to type check. So you can they mostly made it play nice with each other, but yeah, modulo this hack. And this Eta expansion, it's actually used widely in GHC for other purposes, so that wasn't a big deal for the implementation. And the last bit about linear types in general that I will need to show you the actual safe resource management example is how to require the result to be consumed only once, or like how to require linearity on the output instead of the input. And here we can apply the old trick called CPS. So here f wants to return its argument linearly for some reason you want it. And so instead you say, okay, I will not return the argument, and it should be of type B. I will not return you this B. Instead, I accept a function, a linear function from B to R. And so you give it to me, and I will push my result into it, and it will return the result of type R, and I will, forward this R to you. So this is the very, very popular trick. It saves people in many, many places, at least in the functional programming world. And here it also works nicely. So effectively, again, f just returns B, but linearly. So what's important about this example is that it works nicely for monads. So for monads, if you remember the type of bind in particular, it does receive the callback, the continuation, this functional parameter. And so by requiring this parameter to be a linear arrow, you sort of can assert that the result, the value that is dropped into the monad is consumed linearly by its, its client. Yeah, so then, yeah, it inspires a new type called IOL, which is the kind of like IO, but with this linear type sprinkle around the return and bind. And that what allows you to do this safe resource management thing. So I just here, the last bit is that I show that for the do notation, it means that when you do the left arrow, you get the linear value for any linear monad, like IOL in this example, for example. So let's see at least one example. and I'll probably get the second one. I like it more. Yeah, so I say, so here is the file handling mechanism. And here are the, yeah, so let's see both at the program itself and the interface that we use. So I just told you there is this IOL monad, which is kind of like IO, so you can open files, read lines from it, and close files. And yeah, so you get the file path as the input, you open it, and then the read line thing, you know, it has this IOL of something, and something is the linear value. So as we said, the semantics of IOL on the previous slide, I said that the semantics of IOL is that it drops a value, a linear value, a value that you can only use once, and like exactly once. So here you want the handle to be, so it's a pair. So for linear pair, it means that you need to use the handle once exactly, but then the second sort of component of the pair is a unrestricted string. So it means the string that you read, you can use whatever many times you want. There are no restrictions to it. So here we just return it. We could, I don't know, we can return a certain number of iterations of it or concatenations of it. So you have no restrictions on Excel, but you do have a restriction on H. And so if you forget the close file H line here, you will get the type check and error from your compiler, from GHC in this case. It will tell you that the handle has not been, this H thing has not been used exactly once. So you get the new H, sort of fresh H here, and then it just you know, hangs around, and you didn't consume it if you don't close it. So you're, you know, you violate the linearity thing. Yeah, so that's basically it. The third part that I was thinking about, called linear constraints, it's actually built on this example, and I will just tell you what they try to do, and that's it. I will not show you the implementation. So here you will notice you have to thread. So here's this comment about threading, right? So you, for every file handle aware operation, you will have to supply the H and get the new H back. It's how the whole linear typing thing works, basically. And this is really tedious, right? You don't really want to, you know, write a lot of this. So like before in classical file open example, you will just get access. You will not get the H part, and still you can close the file. You would then, you know, use the previous H. But here in the linear world, you have to, every time you have to consume it, because read line really needs the handle. And then you want to close it, so read line also has to return it back. So the linear constraint thing is just an observation that you can be smart about that and build actually a type classes based solution for it, so that compiler figures it out for you. You don't have to carry over this H from every operation to every other one, but still they able to ensure that you do close the file. That's the idea of that later paper about linear constraints. I think I'm up. I'm very sorry about the timing. Yeah, if you have any questions, thoughts, or just comments, I would be happy to hear them.
Oh, well, no worries about taking extra time. I think it was super interesting. I'll open the floor to questions. I don't have any, mostly because I don't know enough to have a good question about this.
Sounds good.
Do you know what's the future of linear types and constraints in Haskell?
Yeah, so as I said, the linear Haskell, the basic extension, has shipped this February. so a lot of people started to experiment with it. There is a bunch of different application libraries on Hackers that tries to use it. They're in their infancy, like in no way they're production ready at this point, I think. But people are looking into it. As for linear constraints, it's highly research experimental phase at this point. So it's, as I said, it's not even published. So I'm not sure. And the paper has several sort of, I would say, questionable design choices. I'm not sure. They probably will have to polish it a little bit more. The basic extension, the linear Haskell extension, go really long road to be accepted to GHC. It took like 2 years to negotiate with the GHC development team, the pull request, and they had to work really a lot on it. But yeah, it seems like now people will start experimenting with it.
Somewhere where this kind of, I don't know, maybe relates to a problem I encounter on a regular basis is I write a lot of code that calls the spin model checker. And usually it's just like, I'll write Python code that calls spin. But spin has very clear side effects. It writes certain files that have the same name every time. And like, if I do 2 spin calls at the same time, then they'll screw with each other because you'll have like 2 files that are called like ___ NBR __ or something like that. And so I end up writing all this complicated code to like use hashes to create folders that don't already exist on the disk. It's, kind of hacky crap like that, which I really don't want to have to deal with. And I've thought about Dockerization, which would be painful and slow things down for no apparent reason. But it would be totally solved if I could just force the model checker itself to be linear, like if I had a linear version of it, because then I wouldn't have to worry that one run of spin was going to read from a temporary file, but at the same time that another run of spin was dealing with that file. So each run could wait for each other. I guess there'd be some complexity about this kind of, like the philosophers eating dinner kind of deal, but that seems entirely solvable. So that's sort of interesting. I wonder if maybe somebody could do a version of spin that somehow allows for some mutex kind of thing so that you get something sort of like linearity.
Yeah, that's a very interesting observation. So you're exactly right that this is kind of a mutex or something that you really pass on to next guy, right? Even if that next guy is the same API call. So like, for example, in this example on the slide, you could call read line twice or thrice, it doesn't matter. You just have to thread the handles, right? Yeah. So that, so then you just, you design the API like that. You hand in the token to your spin thingy, and then it returns you a new token, and then you have to do it. So I think you can perfectly write a linear API you don't even, I don't think you need to re-implement any part of spin. It just, it depends on
it could be a wrapper around spin that was linear. Yeah, that's interesting. Yeah, that might actually be worth my time. I mean, it'd be pretty useful.
Totally. Yeah, I'm not sure how much of name management you can do in terms of sometimes people want fancier names. They want some meaning in those names or something like that. I'm not sure how to it's a good design sort of challenge how to design it nicely, but it does feel like it falls in this category.
Yeah, totally. Cool. Do we have any other questions before we wrap up?
Maybe one more thing. So you mentioned at the beginning that resource-aware stuff is one big use case for linear types. Then another one was writing algorithms that might be easier to get correct if you have linear types. Is there anything else? Is there maybe specifically in Haskell, is there any other application area?
Not that I know of. So they don't even cover the second thing, which is the performance benefits that are advertised, at least were advertised back in the day when people even came up with this idea that we can use linear logic for, at least functional programming languages. So they are actually, I think, like at least there is a lot of demand to reap some benefits from, like the performance benefits from this linear typing and Haskell in particular. And no one really knows, like there are some comments about runtime performance, like runtime performance benefits that you could have, but they are very vague comments. And as far as I know, the main, so there is actually a company that works behind this extension that designed and well, with in collaboration with some researchers, but like there is a main driving force behind this extension, and they say that they don't really look into you know, any performance related stuff, because yeah, I don't know, yeah, it just at first it's hard to like re-engineer the backend, because as I said, it's like at this point it's just the type checking sort of phase that is affected by this, and syntax of course, but like the backend is the very same, and like trying to modify the backend is a really hard problem that no one really knows how to do, I think. So first, the benefits are not really, you know, first they're hard to get, and second, there are probably like lower hanging fruits in terms of optimizing the Haskell compiler. So that's why they don't really look into data, as far as I understand. As far as the other applications, not that I know of. So as I said, so Rust is a really important example how it changed the whole landscape of the languages. But it's like its killer feature is exactly the performance, right? And well, some says correctness, but as I said, like no one really, so they don't have this fancy the monads things, like they don't really, it's a tool of low-level language to you know, design nice high-level protocols with this nice guarantees. So that's what Haskell is better for, I think. But the performance bit they did very well, right? They ditch the garbage collector, and they don't need to manually manage memory as C. So they did, you know, big thing.
Makes sense. Thank you.
Sure.
Cool. Well, thank you very much, Artem. This is quite interesting. It was actually not what I expected, and maybe easier for me to understand than I anticipated, but I appreciate you coming on, and I've got to think more about the potential application to the particular software challenge I'm facing at the moment. So I appreciate your time.
Thanks
unless
a lot
anybody,
for having me.
Yeah, absolutely. Unless anybody here objects, I'll probably put the recording up online so other people can watch it later if they're interested. Artem, is that fine with you?
Yeah, absolutely.
Okay, cool. All right. Well, thank you very much. And I think we'll close up the call.
See you.
Okay.
Bye.
Adios. Bye.